Okay, I'm going to tackle the thorny problem, which I'll call the argument from quantum mechanics for process physics. I'm going to start with Heisenberg's famous quote in his lovely little book, Philosophy and Physics, written in 1958, so well after all his foundational work on quantum mechanics, and he'd had time to think about the philosophy and the implications over an extended period. And he said, in the experiments about atomic events, we have to do with things and facts, with phenomena that are just as real as any phenomena in daily life. But atoms and the elementary particles themselves are not as real. They form a world of potentialities or possibilities rather than one of things or facts, a strange kind of reality, a physical reality, just in the middle between possibility and reality. And I'm going to just try and explore what that actually means in terms of quantum mechanics and how that points or how the meaning of what Heisenberg was talking about here points towards process physics rather than a world of objects. So just to remind you that what I mean by process physics is that the world is not made of a series of discrete objects or the universe. The physical universe is actually a set of processes from which physical objects emerge in our experience, or not just in our experience, but they emerge as apparent, ongoing, stable things that we can call objects. But in order for it to be an object, it has to be the result of an ongoing process through time, as I've argued philosophically. So I'm now going to argue the same case from quantum mechanics, and subsequently I'll make an argument from special relativity. See if I can get this slide to move on. Sometimes it's, whoops, right, there we go. As I said, quantum mechanics challenges the concept that the universe is made up of objects, um, that is, of discrete, independently existing objects with intrinsic properties. So the properties are more relational rather than intrinsic, and this is fits beautifully with the philosophical argument I've talked about. This particular diagram here or illustration is an illustration of the single particle double slit experiment, which I haven't got time to go into great detail here. But the idea is that the emitter of it can be done with electrons, photons. It can even be done with particles as large as quite large molecules, even bigger than buckyballs, which are C60 carbon molecules. Um, but basically, what happens is that you set the emitter at a very low level so that it only emits one particle at a time. That, of course, is an interpretation. It may just be a low field strength at which quantized transfer occurs, and you can see the individual quanta. Whether that's particles is what I'm trying to sort of argue against at the fundamental level. And what happens is that there's two slits, so they can go through either slit. Again, in inverted commas, go through, and inverted commas around they as well. And what happens is you get blip, 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 blip forming on the screen at the beyond the double slits. Here's the screen. But as you continue to wait for longer and longer and longer, so that's going down, the blips end up forming an interference pattern, just like as if you'd had a continuous stream. So if you believe in particles, you've got a problem because the particle, in order to form this typical interference pattern, it would have to interfere with itself and produce these bands of constructive and destructive interference called interference fringes, which is going to come up a little bit later in my talk when I talk about my interference delimitation theory of matter. But anyway, it means that the particles would have had to, each one of those particles, if they are particles, would have had to have gone through both slits, then interfered, and then gone back into particles again when they hit the screen. So that's the so-called wave-particle duality in a nutshell. And I'm going to argue actually that they never were particles, that there is effectively a field set up, whether it's a buckyball field, an electron field, or a photon field, whatever particles in inverted commas, you choose to use. What you're doing is setting up a field, and the particle, what we think of as a particle, is just a quantized emission and then a quantized absorption or arrival of energy in the form of with the properties of what we consider to be an electron or a photon or a buckyball. So that's the wave-particle duality. I've actually done the last thing first. If you remember back to your A-level chemistry, if you're British, or your chemistry lessons, you'll remember that electrons are in orbitals, and you might have been told that they are smeared out electrons and the electron is kind of all over the orbit. But that's not quite true. The orbital is in fact a probability distribution created from Schrodinger's equation, or a variant of, or Dirac's equation, which produces the probability distribution in space. So it's assuming space, and that you in order to sort of draw a line or sort of put a limit around these orbitals, you have to have a probability cutoff, because actually the probability extends throughout the whole universe. It's just very, very low chance that you'll meet the electron. So it's the probability of meeting the electron, these orbitals. And these orbitals obviously give the electron, or it gives the atom volume, because there are certain distances out from the nucleus. And again, of course, volume presumes space. And I'm going to argue away space when we get to relativity, but one thing at a time. We have to think partially spatially. At the moment, I'm trying to destroy your trust in particles as things with definite, or things with volume as we think of volume at the classical level. Solidity, which we've already mentioned in the philosophical section, arises from the fact that these electrons cannot overlap apart from the in pairs, but they cannot have all the same so-called four quantum numbers: the principal quantum number, the spin quantum number, the magnetic quantum number, the azimuthal quantum number. And that so volume as well as solidity arise from the shape and the size of these probability distribution clouds. And I think I could go into more detail about Fermi-Dirac statistics, but I want to try and keep it easy to open to not just to physicists. You know, there's a debate about where mass arises. Everyone thinks that all mass arises from the Higgs mechanism, but in fact it doesn't. The mass of protons and neutrons arises predominantly from the interaction, the strong force, and so on and so forth within the nucleus. Mass seems to arise again from stuff happening, from interactions between particles, perhaps oscillations, resonance states, who knows? I don't think it's fully sorted out. Okay, let's move on to something else. The properties, for example, the position and momentum or spin, only seem to emerge during interactions. Before the interaction, Experiments repeatedly show that there's only a probability, so you don't actually know exactly what position or what momentum. What's even worse is that if you, and I think I'm going to come to this in a subsequent slide, if you measure one, for example, with so-called complementary properties like position and momentum, if you measure one first and then you measure the other, you get a different probability distribution, you get different answers, different sets of probability than if you do the other one first. That's so-called the non-commutable or non-commutation property, or non-commutation feature of paired or complementary properties. So things start to get very strange, and particle behavior, just like with the process philosophy, particle behavior is defined through its interaction with the apparatus. So, for example, if you add a detector at one of these slits, you'll suddenly get rid of the interference pattern, and these electrons will form um, two peaks, as it were, as if they'd just gone through, like particles gone through um, each slit. And if you close one slit, again, you just get the same thing because you lose the interference pattern. So the properties are determined by the experimental setup. Prior to measurement, they only exist, these properties, as outcome probabilities. They do obey conservation laws, but they're not fixed. So momentum has to be transferred, for example, to something else. If the momentum of the electron or whichever particle you're looking at changes, that's got to go somewhere. That's the conservation of momentum, and there's similar conservation laws for energy, for example, for kinetic energy. Particles emerge from conserved properties. Yeah, so I've said that, of interactions, i.e. processes. We've said interactions can't take zero time. So all this undermines the idea of a particle as a persistent object with a definite path. It suggests a process ontology, where events and interactions are fundamental and particles emerge from processes. So I've already talked about the complementary problems. We've talked about the non-commutation, but there's also the fact that if you measure one of these complementary properties, these pairs of complementary properties, the classic one that Heisenberg initially described was position and momentum. There's another one that drops out of Fourier Fourier transforms, which is frequency and time, which may be related to frequency and energy. Sorry, energy and time, because E equals HF. So energy is proportional to frequency, as we've already mentioned. I've mentioned the non-commutation. Yeah, so a lot of people think that Heisenberg's uncertainty principle arises just because it's a problem, a limitation of the measurement apparatus. It's not really a limitation of measurement. It's actually the fact that when you get down to the quantum level, in order to measure something, I mean, you always have to do something to make a measurement, but at the macro level, bouncing a bit of or a lot of light off a solid object is not a problem. It doesn't change the object, but when you're bouncing light off an electron, unfortunately, it changes the electron. So you can't really observe things without interacting with them. That's the problem. So it just indicates that measurement is an interaction, and it implies that measurement determines what actually exists, or that it determines the properties. How you measure it really will give you different answers. That's the key point. The existence of apparent objects emerges from these interactions. So interaction or measurement brings things into being. To exist is to interact. Then there's the thorny problem of quantum entanglement. Without getting too much into detail, this is where two particles, because they have come from the same previous or prior interaction, they are part, if you like, of the same system. And even if they've now become separated by great long distances, um, the properties again of either of these two, let's call them A and B, are not determined until you measure them. And this is, well, I'll talk about how this has been proved. But and then when you measure one of them, you set immediately, instantaneously, you set the state of the other. So this could be two electrons that have come from an interaction, and one of them, in order to conserve angular momentum, one of them has to be so-called spin down, and the other, if one of them is spin down, the other would have to be spin up. Um, and the outcome depends on how they're measured, as I've already said. And in fact, most of the experiments with this have been done on photons for various reasons. But basically, it's what gave rise to Einstein's comment about spooky action at a distance, and his paper with Podolsky and Rosen, the so-called EPR paper, where they sort of talked about the fact that this really just doesn't really make sense in a spatial world, because if affecting one particle A, caused particle B to change instantaneously, it would mean that the influence would travel across space faster than the speed of light. In fact, it would travel instantaneously. We've already said nothing can happen instantaneously anyway, even without invoking the speed of light. So what it means is that, rather like a seesaw, I like to think of it as a seesaw. If one end is up, the other end is one end is up, the other end is down, and vice versa. In other words, the two electrons are actually not two separate electrons. They're part of the same system. They're part of the field, which is so it's not an instantaneous transfer of information, or it's basically that when you measure one, you're also measuring the other one, however far away it is. This comes from experiments, as you know, carried out by Bell and Clauser, who got the not by Bell and Clauser, by Clauser and Alan Aspey, based on Bell's experimental setup, initially a thought experiment, which involves probabilities, and it's a bit complex to explain, and I've forgotten exactly how the explanation works, but it's based on the fact that the probabilities obtained from these experiments show that Bell's inequality is violated, I think. I think it's that way around, which means that the correlations between the two measurements of the two particles they're too closely correlated to be correlated just by chance. They are actually significantly statistically correlated, even though they're far apart. And then probably the real central problem of quantum mechanics, the measurement problem. This is basically the outcome of measurements at the quantum level are predicted by a wave function, which, when you square the answer, or you square, is it the normalized answer, you get a probability distribution, which we've already talked about. And that this probability distribution is not quantized, it's smoothly evolving. It's so-called unitary in the sense that it's a probability that adds up to 1 or 100%. And it's always statistical. When you do the measurements, they're not absolutely specific. They follow probability distributions, just like the particles arriving in these probability bands, these interference bands, but the individual particles seem to be very specific at specific locations. So this has led to the idea of the collapse of the wave function, that in some way this smoothly evolving probability distribution collapses to definite determined outcomes, or not determined, but to definite outcomes. But the problem is that the wave function there's no mathematics or nothing in it that predicts that it will collapse. In fact, the mathematics, as I understand, suggests that it goes on evolving, albeit in a fluctuating, oscillating fashion. It goes on evolving through time in a smooth, continuous way without any sort of quantum jumps. So the individual measurements are not defined or explained by this wave function. The wave function treats the system being measured and the device differently as well. Whereas we know that all measuring apparatus at the end of the day, fundamentally, it's still made up of quantum particles. So what's the justification? So this is the other part of the measurement problem. What is the justification for treating the measurement system as different from the actual quantum system? I think the answer to that is that the measurement system is made up of a highly huge number of quantum particles, which, because they're continuously interacting, they have a much more the wave function decoheres is one of the terms used, but all the wave functions combine and superimpose on each other to give much more definite location to things, which is why probably things are where they are rather than being indefined when we come to measure the edge of an object or the location of an object. So how does process physics explain this? Well, this is my version of how to explain this problem or these problems using using process physics. I've called it the phase transition temporal coherence model. So what I would say is that measurement is not a one-off event, because when, for example, these are silver grains on photographic emulsion or a photographic plate, and this is what happens. This is one of the ways of measuring the outcome, for example, of the single particle double slit experiment, for example, with photons. I can't remember my photography. I think it's silver chloride, and when the photon arrives, it converts that into a silver atom, which then is a definite, and then the atoms accumulate into grains, and those grains are definitely there, and they stay there, and they have definite position. And the original silver atom of the first silver atom of one of those grains has a definite position. So there is this definiteness that seems to have come from this probability distribution. So how can we explain it? What does this phase transition temporal coherence model say? Well, what it says is that those silver grains are still ongoing interactions. They're just ongoing interactions with a much narrower probability distribution. You can think about this if you think about the difference between a silver grain and a phosphorescent screen, which is another way of recording the arrival of the photon or the electron, whatever particle you're using. We're talking about photons at the moment. And that gradually fades, so that's not quite as stable. So the point is that nothing is actually completely 100% definite. There is always a probability that it might change again. It might meet another particle and be reconverted back into silver chloride, or I don't know the chemistry that well. But the point is that the fact that you've got silver atoms there is because there's a new set of ongoing interactions, but with a much higher probability of remaining when you retest and you relook and you keep looking at that silver grain each time you're looking at the very high probability of it still being there, because the probability band, the distribution has got narrower, but it's not completely collapsed. There is no collapse in this model. It's a non-collapse model. The measurement represents a transition from, as I said, a larger to a very much narrower set of potentialities. It's due to a new set of interference patterns where the fringes, if you like, are much more close together, are much more well defined. So it's, if you like, decoherence with the previous system before the particle or the quantum of particle field interacted with the screen, and then ongoing new coherence, which I'm going to argue later on is actually resonance, and that all sort of matter basically is a result of interference patterns with resonance, maintaining these peaks and troughs, which is what gives rise, I think, to orbitals and so on and so forth. So the post-measurement stability comes from this ongoing coherence, new coherence in the new wave interference pattern through time. So that's the temporal coherence. And it behaves like a phase transition. There's a sudden switch. That's where the resonance comes in, because I think what happens is it's a bit like an instrument playing a note in tune with another, and it just resonates and flips to this new set of possibilities, a bit like how water, for example, freezes, a so-called phase transition in physics. I think it's very similar to that. So a new set of ongoing behaviors arise, but they're ongoing behaviors. A silver grain is something that's doing something through time. It has a particular resonance structure of interference. So there's no collapse of the wave function. It's just a different set of superpositions going on. And I think this does solve the measurement problem. So I think process physics is the answer. And there's a kind of overwriting of the old set of probabilities with the new set. And that's how you get this switch, this sudden switch. So I'm beginning to argue, I'm arguing away matter. I've obviously got to I've touched on this interference delimitation theory of matter, which I'm going to come to in a bit more detail. Haven't got rid of space yet. So I think I've done reasonably well in trying to convince you that matter might be processes. So the physical universe, rather than objects, is actually processes. But we've got to sort out, we've got to try and get rid of space next, and that's the really difficult one. And I'm going to do that with an argument from special relativity. But just as an introduction to that, I want to just quote Aristotle. So Aristotle said, movement, rest, figure, magnitude, number, unity, for all these we perceive by movement. This is in De Anima, his book on the soul, interestingly. We perceive by movement, e.g. magnitude of movement. So he said that when we look at something, or we determine its shape and its size and so on, we do it by running our fingers along it. We correlate that with our vision. And Russell Brain took that a little bit further. He was a neurologist in the early 20th century. And he said time plays an important part in our awareness of space. When I bend my elbow, I'm not aware of the movement, but the time taken to effect it. This factor becomes much more important when the whole body moves. Then time is implicit in space, but time is the taken to traverse a distance. So when you walk to the bus stop, or you get in your car and you drive to work, or whatever you do, however you get to work, the space between you and where you're going is really a delay in time over which you're exerting a certain type and amount of energy. If you can fix the way you're doing it, like, for example, light has a very fixed speed, then you can do a direct conversion of space into time, or time into space. And so it's just getting at the idea that maybe all space is like Leibniz thought, it's relational, and it arises from delays in processes. Um, and indeed, as you know, you can express great long cosmic distances as light years, as time. So what I'm going to argue from special relativity, which is going to be a tricky one, is that all space, I'm going to argue really the problems with the current interpretation of special relativity. And I'm going to argue that space arises from delays in time. And yeah, I mean that's basically it. So um, let's just do a little bit more before we get on to the special relativity bit. I'm going to argue that special relativity, that there are problems with the current interpretation, and that a process emergent space arising from time as more fundamental and primary is a better way of understanding the equations of special relativity, which for which Minkowski developed this idea with Einstein of space-time. It's an alternative to space-time, and I'm calling it process emergent space. So just a few other things to sort of, as an intro to that. Time is necessary to measure length or distance, unless you're resorting to a pre-measured measuring rod, but then you've got to say what measured the measuring rod, and you're involved in an infinite regress. Distance can be expressed, as I've said, in light years. Time can be represented as distance on graphs. If you're a physicist, you put time on the y-axis. If you're a normal person, you put time on the x-axis, but you can represent it spatially. So it's just a little clue that time and space, one can be derived, or one can be expressed at least in terms of the other. And that all geometry can be derived from temporal patterns, as we discussed when we said that geometry can be represented algebraically. A line is derived from an increased magnitude, as it were. It's a number getting bigger and bigger over time. You can think of it that way. You can think of a volume or a radius of an expanding sphere. As sort of space emerging from time, which is, I think, roughly how we can think of the universe and the Big Bang. If we want to think of it temporally, we just have to convert that expanding radius into time. So that's where I'm going to leave it, and then I'm going to talk about the problems with I'm going to give a little bit of a background. If you've not done special relativity, I'm going to talk through special relativity. I'm going to talk through the problems with special relativity and in terms of the current interpretations. I'm going to give the process physics alternative and hopefully argue away space as being emergent from time. So I'm going to stop there.